In the silence of the cosmos, something impossible moves. Not a planet orbiting a star, not a comet tracing its long, cold arc through the black. Something stranger, a ghost particle, unseen but relentless, tearing through the fabric of reality at speeds no eye can imagine. Faster than light, faster than fate. A traveler that does not simply break the rules of physics, it shreds them, scattering the fragments into the void. What if such a thing were real? What if the wall we worship, the speed of light itself, is not the end of the road but a fragile illusion, a fence we built to feel safe in a universe that cares nothing for our limits? For more than a century, light has ruled as the cosmic tyrant. Its speed, 300,000 kilometers per second, has been enshrined as the unbreakable limit of motion, the highest velocity possible for matter, energy, or information. Einstein gave us a world bound by that constant, a universe where the speed of light is not only a law of physics, but the very fabric of space-time. Beyond it, we were told, lies nothing. No signal may outrun it. No thought may leap ahead of it.
And yet, deep within the mathematics, something disobedient lurks. In the shadows of equations, there exists a peculiar kind of solution, a particle with imaginary mass. A particle that cannot exist at the speed of light or below it, but must always travel above it. A particle that forever outruns the fastest thing we know, as though it were born on the far side of a wall we cannot breach.
These theoretical specters are called tachyons. Their name comes from the Greek tachys, meaning swift. Swift beyond comprehension. Swift enough to make the laws of physics tremble. If tachyons exist, then nothing we believe about reality is safe. Cause and effect, the bedrock of logic itself, could crumble. Imagine receiving an answer before you ask the question. Imagine a bullet striking before the trigger is pulled. Imagine the future bleeding into the present, the past rewritten by events not yet born. This is the paradoxical universe tachyons suggest. A place where time runs in circles, where destiny might speak to the past, where history itself could be undone. And yet, there is a haunting possibility. What if tachyons are not destroyers but guides? What if they exist not to unravel causality, but to show us that causality is not as simple as we imagine? Perhaps time is not an arrow but a web. Perhaps the future and the past are not separate realms, but parts of the same whole, connected by threads too fine for us to see. To believe in tachyons is to confront the abyss. To deny them is to ignore the shadows at the edge of the map, for they appear again and again in the most unexpected places. In the trembling mathematics of relativity, in the equations of string theory, in the unstable vacuums of quantum fields, always returning like whispers in the dark, as if the universe itself refuses to let the idea die. The consequences of their existence would be staggering. A civilization capable of harnessing tachyons could send messages into the past. Entire histories could be rewritten. The human longing for time travel, for second chances, for redemption of mistakes and reversal of tragedies, it would no longer be fantasy, but physics. And yet, with it would come chaos. The certainty of prediction would dissolve. The universe would no longer be a machine unfolding predictably through time, but a storm of loops, contradictions, and overlapping realities. Still, the allure is undeniable. Humanity has always been drawn to the forbidden, to boundaries set not to be crossed. The edge of the map, the walls of the fortress, the speed of light. All temptations too great to ignore. And so the question lingers, sharper than ever. Are tachyons out there, racing ahead of us, slipping unseen through the cracks of reality? Or are they phantoms, born only of our desire to defy the limits placed upon us? History teaches us caution. Atoms were once speculation. Antimatter was once dismissed as absurd. Neutrinos were once impossible. Each began as scribbles in equations, as dreams in the minds of theorists, as ghosts no one believed in, until they were discovered. Could tachyons follow the same path? Could these faster-than-light phantoms step out of mathematics and into reality? The terror and the hope are inseparable. If tachyons exist, the universe is far stranger, far less stable than we have dared imagine. And yet perhaps it is also more profound. For if time itself is not linear, if causality is not absolute, then perhaps we too are not what we believe. Perhaps free will, destiny and meaning must be reconsidered. Perhaps everything, every choice, every event is part of a pattern more intricate than we can yet see. So we stand at the edge of a question that is both thrilling and terrifying. Are tachyons the messengers of hidden truths or the harbingers of chaos? Are they guides toward a deeper reality or illusions mocking our longing for the impossible? One thing is certain: they will not vanish. They haunt the mathematics too persistently, too elegantly to be dismissed. Even if no experiment has yet revealed them, even if every detector falls silent, tachyons endure in theory, waiting like whispers just beyond hearing. And so the opening question remains, haunting and unresolved. If tachyons are real, what forbidden doors do they unlock? Reality is not what we perceive. It is a fragile illusion, vulnerable to speeds beyond imagination. That is the theme hidden within the idea of tachyons, a statement at once bold, unsettling, and humbling. It suggests that what we call truth, our deepest assumptions about time, space, and causality, is perhaps nothing more than a mirage, a temporary arrangement, ready to collapse under the weight of the impossible. For centuries, humanity has trusted the senses. The sun rises, the sun sets. Objects fall when dropped. The past recedes, the future approaches. This rhythm became our truth, as natural as breath. Science built itself upon this rhythm, codifying the world into laws that seemed eternal. Newton told us that force and motion followed predictable rules. Einstein told us that space and time formed a single fabric, bound together by the speed of light. These laws gave us order. They reassured us that the universe, no matter how vast, could be understood. And yet tachyons stand in the doorway, mocking that certainty. If they are real, then the line between cause and effect is not absolute. The present might be influenced by the future. The arrow of time might not point forward at all. What we believe to be reality might be nothing more than a limited perspective, an illusion carved by our inability to perceive the full shape of existence. The fragility of reality is not a new thought. Philosophers have whispered it for centuries. Plato described the cave, where shadows flickered on stone walls, and the prisoners mistook them for the whole of reality. Descartes imagined a demon deceiving our senses, convincing us that illusions were truth. Even modern thinkers question whether the universe we see is merely a simulation, a projection from deeper layers of reality. Tachyons, though, are not philosophy alone. They are mathematics, they are physics, they are the suggestion that these age-old doubts might be inscribed into the laws of the cosmos itself. In 1967, when Gerald Feinberg first formalized the idea, he did not do so in poetry but in equations. Yet the poetry was there nonetheless, encoded in the implications. For if a particle could exist with imaginary mass, always faster than light, then reality was not fixed. It was contingent, brittle, open to collapse. The bedrock of cause and effect was not stone but ice, thin and cracking. One step too far, and we might plunge into depths we cannot comprehend. The theme is not simply that tachyons are strange. The theme is that tachyons force us to confront the strangeness of everything. If reality depends on light's speed, then what happens when something outruns it? If time depends on cause preceding effect, then what happens when effect precedes cause? If science depends on prediction, then what happens when prediction itself becomes meaningless? To ponder tachyons is to admit that reality is not the fortress we thought it was. It is a tent, fragile in the storm, held upright by rules that may not be permanent. But there is another layer to this theme, one not of terror, but of possibility. If reality is fragile, then it is also flexible. If tachyons exist, perhaps they do not destroy the order of the universe, but reveal a greater order we cannot yet perceive. Perhaps the paradoxes they create are not contradictions at all, but clues pointing to deeper laws. A grandfather paradox might dissolve not in chaos, but in branching timelines. A signal arriving before its emission might be evidence not of nonsense, but of a richer fabric of time, woven in loops rather than lines. And so the theme becomes two-edged: fragility and wonder, terror and hope. Tachyons embody both. They tell us that the universe is less stable than we imagine, and also that it is more profound. This is why the idea persists. This is why tachyons refuse to vanish, even in the absence of evidence. They are more than a hypothesis. They are a metaphor made flesh. They are the embodiment of our deepest suspicion, that reality is not what it seems, that the world we cling to is only the surface of something stranger. When physicists speak of tachyons, they speak in careful terms, measured equations, cautious definitions. But beneath their words lies something older, the human desire to reach beyond limits, to question what seems unbreakable, to peer behind the curtain. Tachyons remind us that every certainty may be temporary, every law provisional, every truth fragile. The theme crystallizes in a single question: what if the impossible is not impossible? What if reality as we know it is only one version of the story, and tachyons are the messengers of a greater narrative? There is both dread and beauty in that thought. Dread because if reality is fragile, then nothing is safe. Not time, not causality, not existence itself. Beauty because fragility means openness, means possibility, means that the universe may hold truths more astonishing than we can yet imagine. And so the theme of tachyons is not merely about physics, it is about us. It is about our willingness to accept that the world is not built to comfort us, but to challenge us. That reality is not stable ground, but shifting tides. That what we see, what we know, what we believe, may all be illusions waiting to collapse at speeds beyond imagination. In the end, the theme is both warning and invitation. Tachyons tell us that the universe is fragile, but they also invite us to explore it anyway. They remind us that truth is not safety. It is risk. It is stepping into the unknown, even when the unknown threatens to undo everything we hold certain. And so the words echo again, now heavier, now filled with resonance. Reality is not what we perceive. It is a fragile illusion, vulnerable to speeds beyond imagination. The silence that follows is not empty. It is heavy, as though the universe itself is waiting for us to decide whether we dare to believe it. For generations, the speed of light has stood as the most sacred boundary in all of physics. 300,000 kilometers per second, no faster, no exception. It is not just a number. It is the foundation of reality itself, the cosmic speed limit written into the very geometry of space and time. To understand why tachyons are so radical, we must first enter the fortress they threaten to breach. Imagine space and time as a single fabric. Einstein showed us this in 1905 with special relativity, and the revelation was staggering. Length and duration, once thought separate, became inseparable threads. Time dilated, length contracted, clocks slowed down, rulers shrank. Yet through all distortions, one thing remained constant: the speed of light. Light was the anchor in a storm, the unbreakable standard by which reality measured itself. This fortress was not built on belief, but on evidence. Countless experiments confirmed it. Subatomic particles hurled to near light speeds in accelerators obeyed its dictates perfectly. Astronomical observations revealed starlight bent by gravity but never outrun. No particle, no signal, no object was ever seen to cross that boundary. In physics, absolutes are rare. This was one of them. It gave us a universe we could understand. If nothing could outrun light, then cause always preceded effect. The arrow of time pointed one way. Energy remained conserved. Paradoxes were sealed away. The fortress of relativity gave us confidence that the universe, however strange, was consistent. But within that fortress, the first cracks began to show. Not in the equations themselves, which remained perfect, but in their implications. The mathematics of relativity allowed for something peculiar. Imaginary numbers slipped in at the margins. Solutions arose that hinted at faster-than-light particles. Einstein dismissed them as unphysical, artifacts to be ignored. Yet the possibility remained, like whispers echoing in the halls of a supposedly impregnable castle. The guardians of physics, its theorists, were both reassured and haunted. Reassured because relativity explained so much. GPS satellites correcting for time dilation, particle lifetimes stretching as they neared light speed, the very existence of E equals mc squared. Haunted because the mathematics refused to silence its own ghosts. Equations do not respect comfort. They do not bow to common sense. They simply speak their truths. And among those truths was the hint of something stranger, something beyond. Here, the figure of Gerald Feinberg enters. A young physicist at Columbia University in the 1960s, Feinberg dared to look directly at what others had dismissed. He asked, what if these ghostly solutions meant something? What if there truly were particles that could never slow to light speed because they already exceeded it? What if reality was not a fortress but a labyrinth, with hidden doors we had only begun to glimpse? But before we leap into Feinberg's vision, we must understand the stakes. For to admit tachyons into the universe is to admit chaos. If they exist, the order we cling to collapses. A message sent faster than light could arrive before it was sent. A cause could follow its effect. A death could precede a birth. Reality, as we know it, would dissolve. And yet, there is seduction in that collapse. For centuries, humanity has longed to transcend time's tyranny, to undo mistakes, to know the future, to escape the prison of causality. Tachyons promise this in whispers. They do not just threaten our fortress, they tempt us to leave it willingly. In this setup, we stand before the walls of Einstein's universe, gazing upward at its strength. We feel the reassurance of its geometry, the elegance of its mathematics, the solidity of its laws. But at the same time we hear something faint, like wind through cracks in the stone. It is the sound of possibility. It is the sound of something moving faster than light. For a century, science has stood firm on this foundation, and yet the very equations that give it strength are also its undoing. Einstein's fortress is not eternal. Within its walls lies the seed of its own collapse, and that seed bears a name: tachyon. Imagine holding a mirror to reality and watching it fracture. Imagine seeing events unfold in reverse, cause dissolving into effect, history running like water uphill. This is what tachyons suggest, not merely new physics, but a new ontology, a new definition of what it means for anything to exist. The setup is not just about the physics, it is about the human condition. We crave stability. We build castles of knowledge, fortresses of certainty, and yet part of us longs for the unknown. Tachyons exploit that longing. They are the crack in the stone, the shadow in the fortress, the whisper that says, nothing is final, not even the laws you trust most. The ordinary world of relativity is not ordinary at all. It is miraculous, wondrous, vast, but it is also finite. It is a map drawn with a boundary, and tachyons, like outlaws, lurk at the edges, daring us to cross. The setup has been built, the fortress stands tall, the speed of light rules supreme. But now we must ask, what happens when the fortress is challenged? What happens when one physicist dares to open the forbidden door? The universe holds its breath. In the year 1967, when the world was already brimming with upheaval, when cultures were tearing down old structures and science was stretching its reach from the atom to the moon, a paper slipped quietly into the bloodstream of physics. Its title was deceptively simple, yet its consequences were incendiary. The author, Gerald Feinberg, a young physicist at Columbia University. Its subject, tachyons. For decades, whispers of faster-than-light solutions had haunted relativity. They were curiosities, dismissed as artifacts of equations pushed beyond their proper domain. To most, they were like mirages shimmering at the edge of mathematics, real only in the way that dreams are real. But Feinberg refused to look away. Instead, he leaned closer. He asked the question others feared to ask. What if these phantoms were real? His paper did not present tachyons as impossible aberrations, but as plausible entities. Hypothetical particles, yes, but with a strange and rigorous logic. They would always travel faster than light. They would never slow down to light speed, just as ordinary matter could never accelerate to it. Their mass would be imaginary, not in the sense of fanciful, but in the precise mathematical sense of involving the square root of -1. They would defy everything we thought immutable, yet they would do so consistently, without contradiction to the mathematics of relativity. It was as if Feinberg had pointed to the cracks in Einstein's fortress and declared, "These are not flaws, but doorways." Imagine the shockwaves rippling through the halls of physics. Faster-than-light particles? Such a thing struck at the very heart of causality. For if information could move faster than light, then cause and effect could be reversed. A message sent today could arrive yesterday. A bullet fired could kill its target before the trigger was pulled. Time, once thought sacred, could unravel. The implications were not merely technical, they were existential. We humans order our lives around time's arrow. We depend on the assurance that past leads to present, present to future. To shatter that arrow is to cast reality into chaos. And yet here was Feinberg calmly laying out the mathematics that said such a world might be possible. This was the catalyst. The moment when an unthinkable possibility became a subject of debate. Tachyons stepped out of the shadows of forgotten equations and onto the stage of serious physics. No longer could they be dismissed as curiosities. No longer could they be ignored. They had been named. They had been given form. The name itself carried power. Tachyon derives from the Greek tachys, meaning swift. Not just faster, but swifter than anything else could ever be. It was a word that carried velocity in its syllables, a word that whispered speed as if conjured by the gods of motion themselves. Feinberg's tachyons were not science fiction. They were science, and that made them dangerous. The physics community responded with a mixture of fascination and alarm. Some saw in tachyons a solution to persistent puzzles in quantum theory. Others recoiled, fearing the collapse of causality. If tachyons existed, time travel was not just a dream, but a potential nightmare. Grandfather paradoxes, logical loops, universes tearing themselves apart. These were no longer the stuff of novels, but the possible consequences of equations brought to life. And yet, despite the dread, there was wonder. What if these particles could be harnessed? What if faster-than-light communication was not fantasy, but reality? Imagine civilizations speaking across galaxies without delay. Imagine warnings sent back in time to avert disasters. Imagine humanity no longer bound by the tyranny of light. The catalyst had been struck, and the fire spread quickly. Physicists debated, papers proliferated, experiments were proposed. Could cosmic rays conceal tachyons? Could particle accelerators, those vast machines of steel and magnetism, birth them fleetingly into existence? Hope and fear intermingled. But perhaps most profound of all was the philosophical rupture. Feinberg's paper forced us to confront the fragility of our assumptions. The laws of physics, which we thought unyielding, were suddenly negotiable. The very fabric of cause and effect, which we thought eternal, was now conditional. If tachyons existed, then reality was not what it seemed. It is difficult to convey the audacity of Feinberg's act. He did not merely write equations, he broke a taboo. He opened a door into a forbidden room of physics, A room filled with paradoxes and spectres, and he invited us inside. Some recoiled. Others entered eagerly, but none could deny the door was there. Picture the world of physics at that moment. A fortress shaken, its stones vibrating with the echo of a single paper. The guardians of orthodoxy clutching their laws, while the dreamers and the rebels leaned toward the abyss. Tachyons were not proven, they were not detected, but they were real in the only way that mattered then. They were imaginable, and once imagined, they could not be erased. The catalyst does not answer questions, it creates them. And Feinberg's tachyons created the most dangerous question of all. What happens if the unbreakable law of the universe is broken? As the paper spread, one thing became clear. The debate would not end quickly. This was no fleeting anomaly. This was an idea too potent, too provocative, too seductive to vanish. It had set the stage for battles that would rage across decades, and so the fortress trembled. Light speed, once absolute, had been challenged. Causality, once sacred, had been questioned. The fortress still stood, but its walls bore the mark of impact. And through that crack, the future, our future, looked suddenly uncertain. For in 1967, Gerald Feinberg did not just publish a paper. He lit a fuse that even now, half a century later, still burns, winding its way toward revelations we can scarcely imagine. The catalyst has struck, the debate has begun, and once the question is asked, are tachyons real? There is no turning back. The spark was lit, and almost immediately the fire spread. Gerald Feinberg's tachyons, born in mathematics and declared plausible in 1967, ignited a debate that cut across physics like a lightning bolt. It was not just a technical quarrel, it was a struggle over the very architecture of reality. On one side were the dreamers, those who gazed into the abyss and saw opportunity. They argued that tachyons might not only exist, but could solve puzzles that had haunted physics for decades. Could these faster-than-light phantoms account for strange anomalies in quantum mechanics? Could they reconcile the irreconcilable quantum uncertainty with relativistic order? For the hopeful, tachyons were not intruders. They were rescuers, waiting in the wings to restore balance to a universe that seemed increasingly fragmented. On the other side stood the skeptics, clutching tightly to the pillars of causality. If tachyons were real, they argued, then cause and effect would dissolve. A message sent from Earth might arrive on Mars before it was ever written. A particle could be destroyed before it was born. Entire histories might be rewritten in a single instant. This was not the rational world of science, but the nightmare of paradox. The debate was not polite, it was fierce. In lecture halls and conferences, in journals and late-night conversations, physicists wrestled with the implications. Some called tachyons elegant, others called them abominations. The more they were discussed, the more urgent the question became. What kind of universe do we live in? At the heart of the debate was Einstein's speed limit, the inviolable law that nothing could move faster than light. To break it was to shatter relativity itself. But defenders of tachyons pointed out something subtle. Relativity did not forbid tachyons outright. The equations allowed them. They simply existed in a different domain, beyond the barrier of light. Just as ordinary matter could never reach light speed from below, tachyons could never slow to it from above. They lived in a realm parallel to ours, forever separated, forever alien. This was the first major revelation in the debate. Tachyons did not violate relativity, they completed it. They were not rule breakers, but rule followers in a higher register. A strange inverted mirror world where the impossible was normal. For the believers, this was exhilarating. For the skeptics, it was terrifying. Philosophers weighed in as well. Some saw in tachyons a metaphor for human longing, our endless desire to outrun the limits of time. Others warned that to embrace such particles was to embrace madness. If the arrow of time could be bent or broken, then the meaning of life itself was at risk. What is a choice if the future can reach back and change the past? What is morality if consequences can precede actions? The debates spiraled into metaphysics as much as physics, entwining equations with existential dread. Yet, amid the arguments, a surprising twist emerged. Tachyons found an unexpected ally in the growing framework of string theory. In the earliest formulations of string theory, tachyons appeared naturally, vibrations of strings that traveled faster than light. To some, this was proof that they could not be ignored. To others, it was evidence that string theory itself was flawed. But either way, tachyons had forced themselves into the discussion of fundamental physics. And then came the paradoxes. The grandfather paradox was invoked endlessly. If tachyons could transmit information backward in time, one could send a message to prevent one's own birth. Logic crumbled, but defenders countered with ingenious loopholes. Perhaps tachyons could never interact with ordinary matter in a way that created paradox. Perhaps the universe itself would enforce consistency, allowing faster-than-light motion but preventing contradiction. Or perhaps we misunderstood causality entirely, and the flow of time was more flexible than we had ever imagined. This was the essence of the debate. Was causality sacred or negotiable? Could the universe tolerate cracks in its order, or would it collapse under the weight of contradiction? Amid this storm, Feinberg himself was careful. He had proposed tachyons not as a declaration of fact, but as a possibility. He was not reckless. He did not claim they had been detected. He simply argued that the equations permitted them. Yet in physics, permission is a dangerous thing. Once something is mathematically possible, the mind demands to know if it is physically real. By the early 1970s, the debate reached fever pitch. Experimentalists wondered if cosmic rays, those mysterious messengers from deep space, might conceal tachyons. Detectors were tuned to hunt for anomalous signals, particles arriving faster than light itself. None were found, but the idea lingered. If tachyons were out there, perhaps they were too elusive, too ghostly to catch. The skeptics grew louder. They argued that tachyons destabilized quantum field theory. They made the vacuum itself unstable, collapsing into runaway energies that defied reason. Unphysical, they declared. Yet the believers countered again. Perhaps the instability was the point. Perhaps tachyons were not particles to be captured, but processes, signs of deeper transitions in the fabric of reality. The debate became almost theological. One camp clung to causality as if it were scripture. The other embraced the chaos, arguing that new laws would emerge beyond the cracks. Both sides knew they were grappling with something larger than tachyons themselves. They were wrestling with the limits of knowledge, the fragility of truth. And then came the public. Science fiction writers seized on tachyons eagerly. Novels and films portrayed them as tools of instant communication across galaxies, as engines of time travel, as weapons of unimaginable power. Popular culture transformed tachyons into symbols of speed and transcendence. For the general public, they became shorthand for the impossible, and so the debate spilled out of the academy and into the imagination of the world. But inside physics, the arguments sharpened further. Were tachyons saviors or saboteurs? Did they reveal new frontiers or threaten the very coherence of science? This was not an abstract quarrel. Careers were built and destroyed on positions taken. Papers were published, refuted, defended. Conferences devolved into shouting matches. The air was electric with urgency. In the end, the debate left no one unchanged. Even those who rejected tachyons outright had to confront the uncomfortable truth. The laws of physics were not as simple, not as stable as once believed. Relativity was powerful but not untouchable. Quantum theory was successful but incomplete, and in that gap between certainty and mystery, tachyons lingered, taunting us with their ghostly promise. The debate was not resolved. It remains unresolved to this day. But it accomplished something profound. It forced us to ask the forbidden questions. It forced us to look at time, causality, and reality with new eyes. Whether tachyons are real or not, they made us confront the limits of what we know and what we dare to imagine. The debate ended where it began, in uncertainty. But it left behind a new trajectory, one that would propel physics deeper into the unknown. And as the arguments burned, one decision emerged from the smoke. We would not turn away. We would follow the trail of tachyons, no matter how treacherous. For the debate had revealed not just fear, but hunger. A hunger for discovery, even if it meant shattering the pillars of reality itself. The choice was made. We would plunge into the abyss. The debate had raged, lines drawn between the defenders of causality and the dreamers of a new order. But at some point, a decision had to be made. Do we turn back, retreating into the safety of what we know? Or do we step forward into the shadows to test whether these spectral beings are waiting for us in the cracks of reality? The decision was made: to search, to risk, to plunge into the abyss. The break was not clean. Physics does not change directions like a sudden lurch of a wheel. Instead, the transformation felt like slipping into an inverted mirror world, where everything familiar seemed skewed. Relativity had taught us that the speed of light was sacred, a wall that nothing could breach. To step beyond it, even conceptually, was to leave the ordinary behind. Yet here we were, peering past the wall, searching for evidence of particles that mocked our foundations. The laboratory became a battleground. Particle accelerators, those colossal machines where protons collide at nearly light speed, were enlisted as hunters. If tachyons existed, perhaps they could be glimpsed in the debris of high-energy collisions. Physicists watched their detectors with religious fervor, scanning for impossible signals, particles that arrived before they should, traces of energy out of step with expectation. The hum of the accelerators took on an almost sinister character, as though these machines were not just probing matter, but whispering to the forbidden. Cosmic rays were another frontier. These messengers from deep space arrive on Earth with energies far greater than anything we can produce in laboratories. Some wondered, could tachyons ride with them? Could they be hidden in the torrents of invisible bullets that rain down on us every second, relics of cataclysms light years away? Instruments were built to catch anomalies, particles that seemed too fast, too elusive. Each false lead only deepened the mystery. And then there were the equations, cold, unyielding, yet strangely fertile. The mathematics of tachyons was not simple. They did not fit neatly into the framework of ordinary particles. They carried what physicists called imaginary mass, a concept that defied intuition. Ordinary mass slowed particles as they gained speed. Tachyon mass, inverted and uncanny, demanded the opposite. They could never slow down below the speed of light. Once born, they were forever faster than light. They were creatures of the beyond, bound not by our rules but by their own inverted law. This was the allure of the new world we had stepped into. It was not simply that tachyons might exist, but that they offered a glimpse into a reality governed by laws that mocked our own. If relativity defined one realm of existence, tachyons seemed to define its shadow. But with this allure came dread. To embrace tachyons was to embrace consequences that could unravel everything. If they could transmit information faster than light, could they also transmit it backward in time? Would free will dissolve into illusion, with the future whispering into the past? Could cause and effect be rewoven into paradox? The closer physicists looked, the more unstable the ground beneath them became, and yet they pressed on. The two worlds had been divided, the safe, stable world of light-speed boundaries, and this new, upside-down realm where tachyons might lurk. The choice to break into the latter was not a quiet one. It was thunderous. It was an act of defiance, a declaration that no law, no matter how sacred, would go untested. In this world, new allies emerged. String theory, still in its infancy, whispered promises of tachyon fields, mathematical hints that faster-than-light states might not just exist, but be necessary. In string theory, tachyons often appeared as signs of instability, heralds that a system was not complete. They were not errors, but signals of deeper truths waiting to be uncovered. Could tachyons then be the messengers of new physics, inviting us to rebuild our models of reality on stronger ground? The hunt was not confined to theory. In the 1970s and 1980s, detectors were built with tachyons in mind. They searched for tracks in cloud chambers and photographic plates that could not be explained by ordinary particles. Some claimed fleeting anomalies, trails that appeared out of nowhere, energy signatures that seemed out of sync with the rest. Were these glimpses of the unthinkable, or just noise, misread data in the chaos of the subatomic storm? The deeper physicists plunged into this world, the more questions emerged. Was it possible that tachyons were all around us, but hidden in a way we could not yet perceive? Could they be moving not through our dimensions, but through unseen ones, brushing past us like ghosts in the walls of reality? The notion was intoxicating. Every failed detection, every null result could be reimagined not as defeat, but as a hint. Perhaps we were looking in the wrong way, in the wrong places. And so the pursuit became philosophical as much as scientific. What does it mean to chase a particle that may never be caught? What does it mean to search for something that might not even belong to our universe in the way we understand it? Some physicists liken the chase to a kind of pilgrimage. Even if tachyons did not exist, the pursuit itself forced us to confront the limits of light, time, and causality. The very act of searching reshaped our sense of what was possible. But in this new world, dangers multiplied. For if tachyons were real, then information could leap faster than light. Messages could be sent not just across space, but across time. Entire systems of security, of communication, of trust in the flow of cause and effect would collapse. The universe would become a theater of paradox, where the future could rewrite the past and the present would crumble in the echo. The stakes could not have been higher, and yet the allure could not be denied. To break into this realm was to risk sanity itself, but to stay behind, to cling to the safety of light-speed boundaries, was to accept ignorance. This was the dividing line. The physics of the known, safe world lay behind us. Ahead was a landscape of shadows and echoes where tachyons whispered possibilities too dangerous to ignore. The choice had been made. We stepped across the threshold into the world where the laws we thought immutable bent, fractured, and threatened to collapse. And in that new world, one truth lingered, unsettling and irresistible. If tachyons are real, then reality itself is negotiable. When the search for tachyons broke away from the safe shores of known physics, another current began to flow beneath the surface. It was quieter, less technical, but perhaps more dangerous. For if tachyons existed, they would not only change equations, they would challenge the very way we imagine time, causality, and even consciousness. And this undercurrent, this deeper story, was always there. The story of humanity's own struggle to find balance in a world built on uncertainty. Every scientific revolution has a hidden twin. The equations unfold on blackboards, the experiments fire off in underground tunnels, but somewhere, often in solitude, a thinker steps back and asks, what does it mean? For neutrons it was stability. For relativity, the malleability of space and time. For tachyons, it was something more elusive, the possibility that reality itself was fragile, that our sense of order might be nothing more than a trick of perspective. Veteran physicists, some with hands calloused from chalk, others with memories of wartime code-breaking or Cold War secrecy, began to frame the tachyon question in human terms. They compared it to the human struggle for meaning, for balance between chaos and order. One physicist remarked that the notion of tachyons moving backward in time was no stranger than the way human memory worked, an invisible bridge between what had been and what was yet to come. If time could bend, perhaps so could thought. The B story then is not about equations. It is about us. It is about the way we stretch for truths that unsettle, the way we dare to imagine faster-than-light messages, while we can barely manage our own tangled histories. Philosophers joined the conversation, pulling tachyons into the domain of metaphysics. They spoke of causality not as a hard law, but as a fragile thread woven through the loom of experience. What would it mean if this thread could be broken? Could a person send a message to their past self, not with words or memory, but with the whisper of a particle? Would destiny become negotiable? Or would we find ourselves trapped in paradoxes where choice collapsed into inevitability? Even mystics found resonance here. For centuries, spiritual traditions had imagined beings or forces beyond the reach of time, angels, messengers, echoes from eternity. Now, physics, that most material of disciplines, hinted at its own spectral messengers. Was the tachyon a scientific version of the angel, carrying information from beyond the boundaries of light? The question was half blasphemy, half revelation. And yet this was not mere fantasy. Some scientists speculated quietly that tachyons might even provide a mechanism for the strangest puzzles of quantum physics. Take entanglement. Two particles separated by vast distances, yet somehow behaving as one. Could tachyons be the messengers here, signals darting backward in time to coordinate the dance? It was speculation, yes, but the kind that teased the edges of sanity. The human story is always about balance. Civilizations rise not through order alone, but through the tension between order and chaos. Individuals, too, are shaped by hidden forces, by doubts and contradictions. The neutron holds the atom together by balancing the repulsion of protons. In its own way, the tachyon became a metaphor for balance too, but a balance stretched to breaking. It symbolized our willingness to entertain the impossible, to flirt with madness for the sake of truth. One physicist described tachyons as philosophy in motion. If they existed, they would embody an idea that haunted thinkers since the ancients, that time itself might not be linear, that the arrow we cling to might bend back upon us. Wasn't this what human memory does every day? Reach backward, rewriting meaning, reframing the past. Wasn't this what regret was, or hope? It is tempting to imagine tachyons as cold, clinical objects, hypothetical data points in equations, but in this deeper story, they are something more. Mirrors. They reflect our longing to know, our fear of uncertainty, our constant push against boundaries. They remind us that science is not just about particles and fields, but about the human drive to make sense of a cosmos that does not easily yield its secrets. Here, then, is the strange gift of tachyons. They force us to think about thinking itself. If information could leap backward through time, what would that mean for the human mind, that strange machine of memory and imagination? Could consciousness itself be a kind of tachyonic process, slipping between past and future, bridging what was and what might be? Some dared to whisper it, others recoiled. But the question lingered, heavy as stone, light as speculation. This was the B story, running in parallel to the equations and detectors. While scientists measured lifetimes and chased anomalies in accelerators, humanity wrestled with the implications. Not just whether tachyons were real, but whether we were ready for what their reality might reveal. It is easy to dismiss such musings as philosophical indulgence, but history teaches otherwise. Every time science has shattered a law we thought absolute, the world has changed, not just in physics, but in art, in literature, in the way we see ourselves. Galileo did not just move Earth, he moved humanity. Darwin did not just sketch evolution, he redefined what it meant to be alive. If tachyons are ever proven real, they too would alter our story, not only how we describe time, but how we inhabit it. For in the end, the search for tachyons is the search for balance, between the known and the unknown, between fear and wonder, between what we believe is fixed and what may yet unravel. Humanity has always walked this line, teetering between madness and discovery. Tachyons, whether real or not, sharpen that edge. And so, as the story presses forward, we must remember, The pursuit of these phantom particles is not just about physics. It is about us. It is about our hunger for meaning in a universe that resists explanation. It is about our willingness to walk into the dark, guided not by certainty, but by the faint glimmer of possibility. Because if tachyons exist, they will not just change our science, they will change our story. Imagine for a moment that the unthinkable is true, that somewhere beyond the shimmering boundary of light's dominion, tachyons sprint through the fabric of reality. What then would such beings of speed and strangeness allow us to see, to do, to become? Here, the mind is set free, and speculation takes on the shape of wonder. For tachyons, if real, would not be just another particle. They would be the undoing and remaking of the universe as we know it. The most immediate possibility is communication. If tachyons could move faster than light, they might carry information not just across vast gulfs of space, but backward through time. The dream, no, the temptation, is to imagine a tachyonic telegraph, a device that whispers warnings to the past, sending signals into yesterday. A civilization armed with such power could prevent disasters before they occur, rewrite choices before they are made, and perhaps even erase mistakes from history itself. What would become of free will if tomorrow could edit today? Would destiny collapse into an infinite loop of revisions? Yet it is not only communication. The universe itself at its deepest levels might pulse with tachyonic threads. Some physicists once speculated that tachyons could emerge near black holes, born from the tearing of space-time itself. If this were true, then tachyons might not only exist, they might be woven into the darkest engines of the cosmos, particles cast into being by the collapse of stars. Imagine black holes not as final prisons, but as furnaces spitting out faster than light sparks, each one a messenger from beyond the event horizon. And what of travel? The tantalizing question, whispered in the halls of speculation, is whether tachyons could become the key to moving not only faster than light, but outside the tyranny of causality. Could a ship in some future epoch ride a tachyonic wind, piercing the gulfs between stars not in decades, but in moments? Could humanity scatter itself across galaxies not by rocket flame, but by hitching itself to a stream of particles born to outrun time? It is an image both intoxicating and terrifying, a cosmos made small, but at the cost of unraveling the arrow of time itself. The playfulness of possibility runs deeper still. Consider quantum entanglement, that strange communion where two particles seem to share a single fate, no matter how far apart they are torn. Tachyons have been invoked at times as the invisible couriers ensuring the dance. If so, then every quantum mystery might conceal a tachyonic secret. The world we take for granted, the screen before you, the matter of your own body, might be stabilized by the silent whispers of faster-than-light messengers ensuring that quantum reality holds together. In such a vision, tachyons are not just exotic curiosities. They are the hidden librarians of the universe, keeping the records aligned across impossible distances. History offers tantalizing echoes of this playful speculation. In 2011, a group of physicists with the Opera experiment announced, briefly and controversially, that they had detected neutrinos traveling faster than light. The claim was withdrawn, an error traced to faulty wiring. But for a brief, electrifying moment, the world imagined it. Particles exceeding light speed, doors to tachyon reality opening. The frenzy, though short-lived, showed how hungry we are for cracks in the wall of certainty. It was a glimpse of the fever tachyons could unleash if they ever stepped into the light. And yet, within the play lies shadow. For what of paradoxes? If tachyons could carry messages to the past, what of the grandfather paradox? Could one warn one's earlier self of danger, thus preventing the very act that required warning? Would the universe knot itself into contradictions, or would it splinter into many worlds, each new choice birthing a divergent reality? If tachyons are real, they might force us to abandon the comforting simplicity of a single timeline, demanding instead a multiverse where every choice is made, every path is taken, and history is an infinite tree branching forever. The fun of speculation is matched only by the dread it awakens. Some theorists suggested that tachyons could be linked to instability, that their presence in equations marked not hidden truths, but collapsing systems. In string theory, tachyons sometimes appear as signals of instability, the universe's way of hinting that a given configuration is doomed. If so, then tachyons are not playful messengers, but omens, not possibilities, but warnings. The fun becomes darker here, to imagine tachyons not as the tools of explorers, but as the fingerprints of universes dying, their equations collapsing into something new. And what of the human dimension? What stories would we tell, what myths would we spin if tachyons entered our grasp? One can imagine religions forming around their strange properties, prophets claiming to send prayers back through time, cults waiting for tachyonic revelations that never arrive. Entire philosophies might rise and fall on the question of whether tomorrow can touch today. For in the end, tachyons are not only about physics, they are about meaning. They are about our endless desire to master time itself. Picture this: a man sitting alone, his life full of regrets. He dreams of sending a single message to his younger self, one phrase that would change everything. If tachyons exist, perhaps he could. But what then? Would the younger self, armed with foreknowledge, avoid those regrets or simply trade them for others? The fun of tachyons is also their tragedy, the idea that even with power over time, we might never escape the burdens of choice, the weight of being human. And this is the promise of the premise. To explore tachyons is to let imagination run wild, to peer into futures both dazzling and dreadful. They could be tools of infinite communication, the seeds of interstellar travel, the custodians of quantum mysteries, or the harbingers of instability. They could be messengers from black holes or errors in our equations. They could free us from time or entrap us in paradoxes we cannot resolve. In this act of speculation, we glimpse both the best and worst of ourselves. Our play is never innocent. It carries with it the shadow of what we might unleash, should tachyons ever prove real. And even now, as we laugh at the what-ifs and marvel at the maybes, a darker truth looms on the horizon. The fun cannot last forever. For at the peak of discovery, at the very height of possibility, comes the turn. And so the question arises: what happens when the evidence turns against us?
There is a moment in every great pursuit when it feels as though the summit has been reached. When all the climbing, the doubt, the struggle seems to vanish into the thin, crystalline air of triumph. For the search for tachyons, that moment came with theory's embrace. The equations themselves seemed to smile, to whisper yes. And for a time, it appeared that the shadows of speculation had finally taken form.
It began within the sprawling framework of string theory. For decades, string theory has promised a unification of the universe's deepest laws, a grand symphony in which gravity, quantum mechanics, and relativity might at last be reconciled. Within that vast, humming orchestra of mathematics, tachyons appeared, not as ghosts, not as mistakes, but as integral notes. They emerged as natural solutions to the equations, particles predicted by the very structure of vibrating strings. Here, in the heart of theory's boldest vision, tachyons seemed to belong. This was the intoxicating high of the midpoint. To those who followed the mathematics, it felt like vindication. If string theory could explain black holes, extra dimensions, and the birth of universes, why not tachyons too? Perhaps they were not fantasies after all, but harbingers of deeper truths, signals that we were glimpsing a reality larger than anything we had dared to imagine. And what a vision it was. In some versions of string theory, tachyons were not anomalies, but agents of transformation. They appeared in unstable systems, announcing the collapse of one false vacuum into a new, more stable universe. In this picture, tachyons were not mistakes to be erased. They were midwives, ushering in the birth of new realities. To see tachyons in an equation was to glimpse a cosmos in labor, preparing to shed one skin and don another. The scale of this revelation was staggering. It suggested that tachyons might not merely exist in some shadowy corner of the particle zoo, but that they might play a central role in the architecture of creation itself. Imagine universes budding from instability, each new world ignited by tachyon fields rolling downhill into stability. It was a picture not of error, but of genesis, and for a time, this felt like victory. The excitement was not confined to string theory alone. Across theoretical physics, hints of tachyons cropped up like sparks in the dark. In quantum field theory, imaginary mass terms, so long treated as mathematical curiosities, were reinterpreted as signs of deeper dynamics. What had once been dismissed as nonsense now looked like evidence of hidden processes at work. Theoretical papers multiplied, each one weaving tachyons into some corner of physics, from cosmology to condensed matter. Everywhere one looked, they seemed to find a home. It was a moment of extraordinary optimism. To skeptics, it looked like overreach, a flight of fancy carried by mathematics divorced from experiment. But to believers, it was nothing less than a revolution in the making. Tachyons, once laughed at as paradoxes, now stood at the heart of the greatest theoretical adventure of the age. And beyond the mathematics, the imagination soared. If tachyons shaped the birth of universes, might they also shape their death? Could the instability they signaled herald not only creation but destruction? Were we even now living in a universe balanced precariously, one day destined to fall through its own tachyonic collapse into something new? The thought was both exhilarating and terrifying, that the very existence of our cosmos might depend on particles we could not even prove existed. But as with all false victories, the triumph carried within it the seeds of downfall. For string theory itself, despite its elegance, remained untested. No experiment had ever confirmed its sprawling predictions, and the more deeply one looked into tachyon fields, the more unsettling they became. They did not represent stability, but instability. They did not reassure us that our equations were complete, but warned us that they might be perched on the edge of collapse. The paradox deepened. To see a tachyon in the mathematics was both a sign of brilliance and of failure. It meant that a system was unstable, doomed to change. Tachyons were not steady truths, but signs of decay. They were the cracks in the walls, the warning tremors before the fall. And yet, the allure remained. For a brief, shining moment, tachyons had been lifted from the shadows and placed at the center of creation's story. They were no longer whispers of paradox, but players in the cosmic symphony. It felt like closure, like the great question had been answered, but in truth, it had not. This was the midpoint, where the story pauses in triumph before the descent into darkness. The questions had not gone away. They had only been deferred. For all the beauty of string theory, for all the mathematical fireworks, there was still no evidence. No experiment had seen a tachyon. No detector had captured their fleeting passage. All we had were equations, fragile, intricate, and untested. And so the false victory loomed large. Physics had embraced tachyons in theory, but reality had not yet confirmed them. Worse, the contradictions in their very nature were beginning to sharpen. If tachyons were real, causality crumbled. If they were imaginary, why did the mathematics cling to them? Were they truths or warnings? Answers or mistakes? It was here, at the height of optimism, that the adversaries began to gather. Skeptics, emboldened by the lack of data, sharpened their critiques. Philosophers warned of paradoxes unresolvable. Experiments returned silence. The victory began to sour. But for a moment, for a fleeting moment, the dream was intoxicating. To glimpse tachyons in the mathematics of creation was to feel, however briefly, that the universe had spoken, that it had lifted a corner of its veil and whispered, yes. And then, just as suddenly, The veil fell again. What if that yes was nothing but a mirage? What if triumph was only the prelude to collapse? The euphoria never lasts. In the story of science, every triumphant ascent carries with it the seeds of collapse. For tachyons, the height of their glory was followed swiftly by the chill of scrutiny, the creeping approach of contradictions that no optimism could erase. The bad guys were closing in, though they bore no weapons of flesh and blood. They came armed instead with data, with skepticism, with the cold precision of experiments that spoke in silence rather than song. The first cracks appeared in the simplest of places, in the detectors that should have seen something, anything, if tachyons were real. Decades of searches, from high-energy collisions in particle accelerators to the watchful eyes scanning cosmic rays, had yielded nothing. No tachyon tracks etched in bubble chambers, no anomalous signatures whispering of faster-than-light messengers. Nothing but silence. And silence, in science, is as damning as a verdict. Then came the contradictions in decay. The neutron, the proton, the pion, each particle with a lifetime measured and remeasured. If tachyons existed, some decay products should have betrayed their presence, leaving imprints that bent the expected distributions. But no such anomalies emerged. The statistics held steady, the predictions matched reality. Tachyons, if they were there, left no trace. The absence was deafening. It was here that doubt grew teeth. Physicists began to mutter that perhaps tachyons were not misunderstood truths, but mathematical phantoms, artifacts of equations stretched beyond their domain. Stephen Hawking himself poured cold water on the speculation, warning that faster-than-light travel, whether by particles or spacecraft, led inevitably to paradox. Causality, the bedrock of science, could not survive tachyons. And a universe without causality is not a universe in which science can function. The bad guys were not villains, not in the comic sense. They were guardians, defenders of order against the encroaching madness of speculation. Their argument was simple. Tachyons were too dangerous to exist. If they were real, time itself would unravel. If you could send signals into the past, then the consistency of reality would dissolve. The grandfather paradox, so often invoked as a thought experiment, would become an inevitability. Kill the past, erase the present, destroy the future. Such a universe could not hold. And yet, the mathematics remained seductive. Theories continued to whisper of tachyons, refusing to let them go. They appeared in string theory as signs of instability. They cropped up in quantum fields as imaginary mass terms. They haunted the equations like ghosts refusing to be exorcised. But skeptics pointed out that instability was not a confirmation of existence. It was, if anything, a reason to doubt. A universe riddled with tachyons would collapse before it could begin. Their presence, some argued, was not proof of reality, but evidence of a model's failure. This was the tightening of the net. Theory lured us forward, but experiment pulled us back. The Large Hadron Collider, the world's most powerful machine, smashed protons together with energies beyond imagining, probing the smallest scales of reality. If tachyons were lurking anywhere, the LHC should have seen them. But again, nothing. The detectors returned data that matched the standard model almost perfectly. The silence deepened, and with silence came despair. For the longer tachyons refused to appear, the more their very concept began to rot. What kind of particle exists only in equations, but never in reality? How long can a ghost remain before we admit it was only a trick of the light? The philosophical dread sharpened too. If tachyons are real, then causality collapses. If they are not real, then why do our theories conjure them again and again? In both cases, there is discomfort, a sense that something fundamental is wrong. It was not only a scientific question now, but an existential one. Were we chasing shadows because we longed for them, because the idea of faster-than-light particles seduced us with its promise of breaking free from time's tyranny? Or were those shadows pointing to a truth too terrible to face? The contradictions multiplied. Tachyons implied infinite energy requirements. Moving slower would require more energy, not less. They violated the principle of locality, suggesting effects before causes. They undermined relativity, the most well-tested theory in physics. Each new objection was like another stone placed on the chest, slowly pressing the breath from the dream. And yet hope clung to the edges. A few physicists whispered of hidden sectors, of tachyons confined to dimensions beyond our reach. Others speculated they might manifest only under cosmic conditions, near black holes, or in the first instance after the Big Bang. Perhaps our machines, vast though they seemed, were simply blind to them. Perhaps silence was not absence, but limitation. Still, the mood shifted. The false victory at the midpoint was fading into the darkness of realization. The bad guys, the critics, the skeptics, the defenders of order, were not wrong to demand evidence. And the evidence was absent. Everywhere they looked, tachyons were not. This was the tightening spiral, the sense of inevitability closing in. For a moment it had felt as though tachyons might rewrite the cosmos, that they might be the messengers from beyond light. But now, with each failed experiment, each sharpened critique, the dream was beginning to collapse. And so the stage was set for the next act. The optimism of theory had been strangled by the silence of data. The promise of revelation had curdled into doubt. The bad guys had closed in, and the dream was gasping for air. But what happens when the dream finally dies? Every great pursuit eventually collides with its own limits. For tachyons, that collision came not with a flash of revelation, but with silence, prolonged, unyielding silence. It was the kind of silence that feels like an answer in itself. By now, the optimism of earlier decades had been drained. Each attempt to glimpse tachyons had ended in disappointment. Each experiment that might have uncovered traces of faster-than-light particles instead returned results comfortably aligned with existing physics. The Large Hadron Collider, with its sprawling detectors and unimaginable energies, revealed the Higgs boson as predicted. But no tachyons, no deviations, no anomalies whispering of instability or paradox. This was the whiff of death, the moment when scientists began to ask the question they dread. Were tachyons never real to begin with? Were they only mirages conjured by equations, reflections of instability mistaken for possibility? The sense of collapse deepened in the mathematics itself. For those who had placed hope in string theory's tachyon fields, the hard truth was that tachyons did not signal promise. They signaled failure. A tachyon in an equation did not mean reality was revealing itself. It meant the model was unstable, doomed to collapse into something else. In this sense, tachyons were not heralds of discovery, but omens of breakdown. Their presence told physicists, "You are standing on the wrong ground. This is not the true structure of reality. Move on." It was a cruel reversal. Once, the appearance of tachyons in theory had been intoxicating, a sign of hidden dynamics at play. Now the same presence was regarded with suspicion, even disdain. Instead of doors, tachyons had become dead ends. The despair spread. One could hear it in the tone of papers and conferences, where once bold speculation now turned cautious, even cynical. The dream of faster-than-light particles, of information whispered backward through time, had withered into a cautionary tale. It was no longer a frontier, but a warning against chasing shadows. And then came the philosophical reckoning. If tachyons were never real, what did that say about our theories, about the human desire to believe in them? Why had so many clung to the idea, even as evidence refused to cooperate? Perhaps tachyons revealed more about us than about the universe. Perhaps they were reflections of our longing to escape time, to transcend causality, to rewrite our own mistakes. Perhaps the tachyon was not a particle at all, but a mirror held up to humanity's deepest desires. This was the heart of the all is lost moment. The dream was dying, and with it, something larger seemed to be slipping away, the audacity to imagine a universe stranger than what the evidence allowed. For without tachyons, the cosmos felt smaller, less mysterious. Time remained a straight line. Causality remained inviolate. Light retained its crown as the ultimate speed. The forbidden door was closed, perhaps forever. The imagery of collapse was everywhere. In lecture halls, diagrams of tachyonic mass terms were presented not as possibilities, but as examples of instability, mistakes in need of correction. In discussions of relativity, tachyons were treated as paradoxes, logical impossibilities that only proved the strength of Einstein's theory by their very absence. Equations that once shimmered with the possibility of faster-than-light messengers now lay discarded, as if abandoned relics from a dream that had soured. And the human dimension of loss could not be ignored. Young physicists who once daydreamed about tachyonic travel now turned their attention elsewhere, to dark matter, to quantum computing, to gravitational waves. The great river of curiosity had flowed on, leaving tachyons as an eddy, stagnant and forgotten. For the world had little patience with ideas that could not bear fruit. But perhaps the sharpest wound was existential. The idea that tachyons might exist had carried with it the thrill of possibility, the sense that the universe was not bound by the limits we thought unbreakable. Their absence was not just a scientific disappointment, it was a blow to the imagination, a reminder of how small and confined our reality might truly be. The dream of transcending time, of breaking free from causality, was not just fading, it was being buried. There are moments in human history when hope collapses into dust, when the very act of dreaming feels foolish. For tachyons, this was that moment. To believe in them now was to risk ridicule, to be accused of indulging in fantasy rather than science. The journals closed their doors, the conferences moved on, the energy shifted elsewhere. And yet, in the depths of despair, something stirred. For there is always a residue, even when the dream seems dead. A handful of voices still whispered, still wondered. Was this truly the end? Or was it only a passage, a darkness before another kind of dawn? But those voices were faint. The consensus was clear. Tachyons had been a beautiful mistake, a shimmering mirage that had led us astray. The pursuit had been noble, perhaps even necessary, but it was over. And in the silence that followed, there was a heaviness, a grief that reached beyond physics into the very heart of what it means to search, to hope, to believe. The dream was gone, or so it seemed. What could possibly emerge from this void? The silence was crushing. The dream of tachyons had collapsed beneath the weight of failed experiments, paradoxes too wild to tame, and equations that whispered instability rather than promise. For those who had dared to believe, it was a season of mourning. The universe, once imagined as strange enough to hold faster-than-light phantoms, now seemed smaller, colder, more indifferent. In this dark night of the soul, physics itself felt diminished. What was left when imagination had been punished, when the forbidden doors slammed shut? Time, relentless and linear. Light, unyielding in its supremacy. Cause and effect, chained in endless succession. A universe, tidy and predictable, stripped of its wildest possibilities. But beneath the despair, something deeper stirred. A quiet, uncomfortable truth. For even as tachyons seemed to vanish from credibility, hints and whispers remained, embedded in the very fabric of our science. They lingered like embers in the ashes, faint but refusing to die. Consider quantum entanglement. Two particles, torn apart, somehow still behaving as though they were one, signals that seemed to defy distance, coordination that seemed instantaneous. Could such a phenomenon really exist without some faster-than-light mechanism at work? Many dismissed the thought, pointing to non-locality as a mathematical trick. But others wondered, was it not possible that tachyons, silent, unseen, were the hidden messengers of quantum reality, darting between particles, stitching their fates together in defiance of space? And what of the early universe? In the first instant after the Big Bang, as energy boiled and space inflated, some cosmologists suggested that tachyon-like fields may have played a role. Fields that collapsed, driving inflation, seeding the cosmos we inhabit today. Perhaps tachyons had existed not as particles to be trapped in detectors, but as processes, fleeting, powerful, gone before we ever had the chance to observe. If so, then tachyons were not fantasies. They were our ancestors, midwives of reality itself. This was the paradox of the dark night. Tachyons seemed impossible, yet their fingerprints were scattered across the puzzles that still haunted science. The very anomalies we struggle to explain, dark energy, quantum non-locality, the arrow of time, felt like echoes of something beyond the reach of current understanding. Perhaps tachyons were never meant to be seen directly. Perhaps their role was to lurk in the background, shaping what we couldn't explain, like shadows reminding us that light is not the whole story. Still, the despair weighed heavy. For physicists trained to demand evidence, whispers were not enough. What good was a dream if it could not be proven? The field had moved on, drawn to safer mysteries, to problems that promised solvable puzzles rather than paradoxes. Tachyons remained on the fringe, abandoned, their name invoked more often in science fiction than in serious journals. But here, in the depths of abandonment, philosophy began to seep back in. If tachyons were not real particles, could they at least be symbols? Could they represent something larger about our relationship with reality? The human longing to undo mistakes, to escape the tyranny of time, to send messages to our former selves, all these were bound up in the dream of tachyons. Perhaps, even in their absence, they revealed something vital about us. It is in the darkness that reflection sharpens. Without tachyons, the universe seemed stable, predictable, safe. But was safety really what we wanted? Or did we secretly long for danger, for paradox, for the thrill of a cosmos that resisted domestication? The death of tachyons was not just the end of a hypothesis, it was the loss of wonder, and that loss cut deeper than many dared admit. Yet history reminds us that science has always risen from such nights. Once atoms themselves were only philosophy, dismissed as unprovable speculation. Once black holes were considered absurdities, mathematical curiosities with no basis in reality. Once the Higgs boson was called the God particle, as if to mock its improbability. Again and again, what seemed impossible emerged as truth. Could tachyons one day follow that path? Could their current burial be only a prelude to resurrection? Hints continued to emerge in obscure corners, anomalies in neutrino data, equations in quantum gravity that refused to expel tachyonic terms. Even in string theory, though many used tachyons as signs of instability, some whispered that instability itself was a clue, that the universe was never meant to be perfectly stable, that decay and transformation were its true foundations. If so, then tachyons were not failures. They were the essence of change. This is the strange gift of the dark night. It forces us to see differently, to strip away the illusions, the false victories, the comforting lies. What remains when the dream is gone is raw truth. And the truth may be this: tachyons are not particles to be found in detectors. They are processes, transformations, reminders that reality itself is unstable, dynamic, forever in motion. The absence of evidence is not necessarily evidence of absence. Sometimes it is the universe telling us to look differently, to think more deeply, to stop demanding that reality conform to our narrow expectations. The despair did not vanish, but it began to transform. In the silence of failure, in the weight of disappointment, a new possibility flickered. Perhaps tachyons were not dead after all. Perhaps they had only shed the form we expected. Perhaps they were not things, but metaphors, keys to truths we had only begun to glimpse. And so, in the long night, a new dawn stirred faintly on the horizon. For even at the lowest point, the question remained, nagging, insistent, unkillable. What if tachyons are real, not as particles but as revelations? From the shadows of disappointment, a fragile clarity began to emerge. Tachyons, once mocked as phantoms, dismissed as paradoxes, refused to die. They persisted, not in detectors or accelerators, not in the neat columns of experimental results, but in the questions themselves. Every time science tried to bury them, the outline of their ghost returned, traced in the margins of theory, whispered in the anomalies that refused to resolve. And so, slowly, a revelation unfolded. Tachyons were not things to be hunted, not marbles to be trapped in glass jars. They were processes, they were signs, they were the language of instability, the mathematics of transformation. In string theory, tachyons often appeared as warnings, symbols of an unstable vacuum, of a reality perched on the edge of collapse. For decades, physicists took this as failure. But what if instability was not a flaw? What if it was the foundation? In a universe where stars live only by burning themselves away, where matter itself decays, where even protons may one day crumble, perhaps the tachyon was not an intruder. Perhaps it was a mirror, showing us what reality truly is. Not permanence, but persistence. Not stillness, but motion. This realization marked the break into a new way of thinking. The old dichotomies, real or unreal, proven or disproven, were abandoned. In their place arose a synthesis, tachyons as metaphors, as processes, as tools that forced us to reimagine. They were the collapse of stability itself, the reminder that nothing lasts. And yet in that impermanence lies the very engine of creation. Consider the early universe again. Tachyonic fields may have driven inflation, a moment when space itself expanded faster than light, carving the universe from nothing in a fraction of a second. If this was true, then tachyons were not failures of theory. They were architects of reality, hidden in the first heartbeat of time. They were gone now, yes, but only because their work was complete. They were scaffolding removed once the structure of the cosmos stood on its own. This was the profound reframing. Tachyons as events, not particles. They were transitions, not destinations. Every decay, every transformation, every crack in the facade of permanence carried their signature. To speak of tachyons was to speak of change itself. But the synthesis did not stop with physics. Philosophy began to entwine with science, weaving a tapestry that reached deeper than equations. If tachyons existed only as processes, what did that say about us? About consciousness, about life? We too are processes, not things. Every cell in our bodies is replaced, every atom borrowed and returned, every thought a flicker that vanishes the moment it arrives. Like tachyons, we are not permanent. We are storms, held together only by the interplay of forces, surviving not by stability, but by constant transformation. To live is to decay, and in decay, to endure.
Suddenly the mockery of tachyons transformed into a mirror of the human condition. What we feared in them, that they could not be grasped, that they mocked causality, that they refused permanence, was exactly what we feared in ourselves. We fear our own instability, our own fragility, our own fleeting nature. Yet, like tachyons, perhaps our reality is not defined by being things, but by being processes that leave traces, impacts, ripples across time. It was here that despair gave way to awe. The death of tachyons was no death at all, it was metamorphosis. What had seemed like failure was, in truth, transformation into something greater. In laboratories, equations still gave hints of their presence. In string theory's strange landscapes, tachyonic fields pointed toward universes beyond our comprehension.
In quantum puzzles like entanglement, the logic of faster-than-light whispers still stirred. The shadows remained. But now, we no longer demanded that they step into the light. Their very refusal to appear was the message. Tachyons were never meant to be caught. They were meant to teach, to remind us that the universe is not a stable block of reality, but a shifting storm, fragile yet enduring, mysterious yet knowable in glimpses. And so science and philosophy, estranged siblings, came together again. Physics admitted that its most unsettling symbols could not be banished. Philosophy embraced that reality was stranger than language could hold. In this reunion, tachyons took their place not as answers, but as provocations. They were not endpoints, they were beginnings. From the dark night, then, emerged dawn. No longer was the question framed as are tachyons real, but rather, what do tachyons reveal about reality? This was the synthesis, the shift into a new act, a new purpose. The narrator's voice deepens with weight. If tachyons are not things but storms, not particles but processes, then what else in our universe might demand the same reframing? What else do we mistake for permanence, when in truth it is only pattern? The cliffhanger approaches like thunder. What if everything we know, matter, time, even ourselves, is only tachyonic, not solid, not eternal, but storms flickering on the edge of decay? The storm had been building across the narrative, the winds of uncertainty gathering with every contradiction, every failure, every glimpse of possibility. Now it broke in full force. The finale was not a neat resolution, not a tidy equation that restored order. Instead, it was confrontation between what we thought reality was and what it might truly be. Tachyons, once treated as absurdities, revealed themselves as more than rumors in the mathematics of the cosmos. They had been in some ways the shadow companions of our most profound discoveries. When relativity claimed that nothing could outrun light, tachyons lingered in the margins, mocking the absoluteness of the claim. When quantum mechanics revealed entanglement, instantaneous and mysterious, tachyons whispered as the uninvited explanation, the messengers darting through the void. And when string theory expanded our reality into hidden dimensions, tachyons appeared as guides, pointing not to stability, but to the creative chaos of collapse. It was in this final act that the reframing found its power. Tachyons were no longer hunted particles, but forces of transformation. The very fact that they appeared in theories as harbingers of instability, signaling that the ground beneath our feet was not firm, meant that they were indispensable. They taught us that instability was not a failure, but the pulse of the universe. Stars lived and died by it. Black holes thrived on it. Galaxies spun only because of it. Life itself, fragile and temporary, endured only because of its restless churn. In that sense, tachyons were everywhere. Not as particles streaking faster than light, but as the logic of impermanence that made everything possible. Without instability, there would be no creation, no birth, no evolution. The cosmos would be static, lifeless, frozen into eternal symmetry. But symmetry breaks. Stability collapses. From the fall emerges the storm, and from the storm comes new worlds. The scientific threads reached their climax here. Tachyon condensation, a feature of string theory once seen as a defect, became the key to understanding how universes stabilize. In this view, tachyons were not warnings of failure, but the very mechanism by which one false vacuum gave way to a truer one. They were the hammer that shattered illusions so new realities could take shape. Without them, our cosmos might never have emerged from the void. They were not the villains of physics, they were the midwives. And so, the storm of tachyons was not destruction, but creation. Each collapse was a genesis, each instability was a doorway. The finale became clear. To understand tachyons was not to pin them down in accelerators or equations, but to recognize them in every act of transformation the universe performs. Philosophy found its answer too. The old question, are tachyons real, shifted into something richer. Reality itself was reframed. If tachyons were processes, not things, then perhaps everything we call real is the same. Not fixed objects, but patterns of interaction, storms of matter and energy that endure only because they change. A rock seems solid, but it is a tempest of atoms, a churning of particles bound together in tension. A human life seems stable, but it is nothing more than a flow of memories, cells, breaths, a storm that flickers and fades. Even the stars, eternal to our eyes, are only burning storms balanced on the edge of collapse. The finale thundered with this revelation: permanence is an illusion. Change is the only law. Tachyons, whether they exist or not, had forced us to see it, and yet awe lingers in the possibility that they might still be out there, hidden in higher dimensions or buried in the first instance of cosmic time. If they are, then the keys to time itself may still lie within their grasp. They might connect the impossible threads of entanglement, whispering across the void in defiance of causality. They might be the heralds of universes beyond our own, reshaping reality every time symmetry shatters. The storm reached its peak as science and philosophy, once divided, fused into a single voice. Tachyons had shown us that our deepest fears, the collapse of certainty, the fragility of permanence, the inevitability of decay, were not weaknesses of the universe but its strength. Reality was not fragile. It was flexible, not rigid, but resilient. Its storms did not destroy, they renewed. This was the triumph of the finale, to look into the abyss, into the chaos of faster-than-light ghosts and broken equations, and to find not despair but transformation. The castle had been stormed, the old illusions lay in ruins, and in their place stood something more profound, a universe alive with processes, not things, storms, not statues, change, not permanence. The voice falls to a whisper, the storm subsiding but leaving its mark. Tachyons may never be found in a detector. They may never streak through a chamber or leave a trail on film. But they have already reshaped the way we think, forcing us to confront reality's most dangerous secret, that nothing is permanent and that in the collapse we find creation. The closing beat of the finale hovers, unresolved but inevitable. If tachyons are storms of transformation, what storms are we? The cosmos opens once more. The same vast, ink-black canvas we glimpsed at the beginning returns, but now it feels transformed. In the opening it was silence, emptiness, a stage upon which we dared to imagine faster-than-light phantoms slipping through the cracks of reality. Now, after the storm of inquiry, the void is not silent at all. It hums, it breathes, it pulses with unseen storms that may be tachyons, or perhaps the very laws of transformation that govern everything. A thread of light cuts across the darkness, not as a beam traveling forward, but as something fractured, bending, refracting, shimmering with possibility. It no longer feels like a simple ray of photons. It feels like a question mark drawn across eternity. We are reminded that this light, which once seemed to be the absolute ruler of reality, may itself be only one part of a greater story. If tachyons exist, if they truly outrun light, if they defy causality, then the universe is far stranger than we ever dared to believe. But even if they do not, their ghost has altered us. By imagining them, by wrestling with their impossible implications, we have opened ourselves to a deeper truth, that reality is not a fortress but a storm. The final image is not of particles themselves, but of patterns, the swirling galaxies, the dance of atoms, the pulse of stars. They all echo the same lesson. Everything is temporary, everything is born from instability. The neutron, the proton, the hadron, the quark, they endure only because they are balanced storms, patterns of forces that can collapse at any moment. To be real is not to be permanent. To be real is to persist, however briefly, against the pull of decay. And so we return to ourselves. a hand resting on a stone, a breath fogging in the cold, a memory flickering in the brain's delicate storm of firing neurons, all of it fragile, all of it impermanent, and yet all of it real, not because it lasts forever, but because it exists in the now, because it holds itself together for as long as it can. Tachyons, in their strange way, have taught us this. They remind us that the universe does not promise stability. It promises only change. The faster-than-light ghosts lurking in our equations are metaphors for the restless heart of reality. They may never be caught. They may never leave a trail in a detector, but they reveal what we are too often blind to see, that existence itself is a balance on the edge of collapse. This is the final image, storms within storms. A universe alive not because it resists change, but because it thrives on it. The stars above us burning only because their cores are unstable. The earth beneath us solid only because atomic storms refuse to collapse. And we ourselves, creatures of thought and breath, enduring only because our own storms of matter and memory have not yet dispersed. The silence of space deepens, but it is no longer emptiness. It is possibility. Every whisper of instability might be a tachyon, rushing backward through time. Every collapse might be the birth of something new. Every death might be a doorway. And so the last words hover like a challenge across the cosmos. If tachyons are real, then reality itself is far more fluid than we can ever know. If they are not, then their ghost has already done its work, reshaping the way we think, reminding us that permanence is a mirage. Either way, the question lingers. Are tachyons even real? Perhaps the answer is not in the detection, nor in the proof, but in the pursuit. For in chasing them, we learn what it means to exist in a universe where nothing stands still, where even light itself may not be the ultimate speed limit. The final image lingers, cosmic storms, human storms, all balanced on the edge of decay, all alive precisely because they are fleeting. And in the silence after, as the stars blaze in fragile defiance of darkness, we are left with the question that refuses to die. If even the tachyon is only a storm, what does that make us? The stage is dark again, but not silent. It feels as though the universe itself is holding its breath, as though something unseen is listening to us. We have spoken of tachyons as though they are specters, phantoms of equations, mathematical stowaways hiding in the margins of physics, and yet they linger in the mind like mischievous spirits who refuse to leave. Perhaps that is their true role, to haunt us, to push us, to remind us that the cosmos is never finished, never settled. Imagine for a moment that tachyons are real, but they are laughing at us from behind the curtain of reality. They run backward through time, slipping between events before we even know they're gone, giggling like children escaping their parents' grasp. To us, they are invisible. To them, we are lumbering statues moving painfully slowly through a universe they see as fluid. For tachyons, our laws of physics are quaint little stories, fairy tales that collapse the moment you read them too closely, and yet, perhaps they envy us. We, who live within the prison of causality, are granted something they can never know: the arrow of time. A story with a beginning, a middle, and an end. For all their speed, for all their freedom, maybe tachyons can never sit still long enough to feel the warmth of a sunrise, the weight of a hand in theirs, or the slow unfolding of a lifetime. In this way, tachyons are not just science fiction, they are parables. They are the universe whispering riddles about itself. They are cosmic tricksters, daring us to question whether time itself is real or only a construct of our fragile perception. But here is the most unsettling thought. What if our very act of wondering about tachyons makes them real? What if, in imagining them, we have already given them form, invited them into the collective storm of human consciousness, etched them into the great library of ideas that shapes how we see the cosmos? In chasing them through equations and accelerators, perhaps we have conjured them, not in detectors but in ourselves. The irony then is delicious. Whether or not tachyons exist in some hidden dimension, they already live in us, in our questions, in our restless drive to reach beyond what is safe, to break the limits, to seek the forbidden door. In that sense, they are as real as any proton, neutron, or photon. They may not be in our instruments, but they are in our imagination. And imagination is what bends the future. So we end not with certainty but with play, with the strange joy of knowing that the universe is not a closed book, but a trickster's riddle. Perhaps tachyons are laughing at us even now, moving faster than our thoughts, rewriting the story behind our backs. Or perhaps they are nothing more than a carnival mirror, showing us how fragile our reality is, how temporary even our most sacred laws might be.
Either way, they serve their purpose. They make us dream of what lies beyond the edge of light. They make us see the cracks in the fortress of causality. They make us wonder what else is hiding in the darkness, waiting to be imagined.
And as the screen fades to black, a final echo remains. Not an answer, not a proof, but a dare. What if tachyons are not only real, but laughing at us still? Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.